Good morning. Happy Monday. How's everybody doing today? Say hello in the chat if you're here. Otherwise, welcome if you're watching it later. So let's see, where do I want to start? I caught up on grading, so that was good. So double check your exams. Make sure that, you don't have something funky. I try to be generous with like any spelling errors, or if how when you don't exactly follow the directions, like it's looking for a number answer and you accidentally put, some text after. If you have any errors like that, just get them fixed ASAP. And let's go over the lab before jumping into this week. Let's see if I can find, I think it was lab 6 where I was seeing some issues. Sorry, trying to find it. Yes, it was lab 6. And so let's look at that one. And let's actually try the post-lab question, because a lot of people got that wrong, at least the ones that I've graded so far. And so this is related to our moles chapter. It's a pretty important chapter. And so let's kind of break down what it's saying. So we have here a student heats 4.75 grams of copper 2 sulfate pentahydrate in order to drive off the waters of hydration. And at the end of the experiment, the mass of anhydrous copper sulfate is determined to be blah. And so write the balanced equation for this process. Use that to calculate the theoretical yield. And then from there, the percent yield. And so let's think about this. And so I think some people didn't really start off by writing a balanced equation first. And so that's what we needed to do. And thinking about what this process is. So we have copper sulfate pentahydrate. And then in our balanced equation, right, the product is the anhydrous copper sulfate. And anhydrous just means no water. And then plus our 5 equivalents of H2O. And so we had to set up this equation. And then from there, we should treat it like one of our normal stoichiometry problems. And so what I mean by that is we have this, right, 4.75 grams. And so let's go ahead and get the molecular weight of both the pentahydrate. So, and so you can tell what I mean. So I'm going to probably, I'm going to say cheat a little. So copper. So you can add it up, or I'm going to look at Wikipedia to make this a little faster for myself. And so make sure you look at the molecular weight. So that gives you both the anhydrous and the pentahydrate. So if you added it up by hand, just double check that you had these right numbers. Although I didn't really see anybody having that as the issue. Again, at least the ones that I graded. So 159.60 grams for the anhydrous, and then the pentahydrate is 259.685 moles. And so we can do this a couple of different ways. So I would encourage you to just treat this like a mole problem. And so let's find, right, the moles. So that's what we're going to do. So we're going to divide. So we said that 1 mole of copper sulfate pentahydrate is 249 grams. And that gives us our moles. Then they're in a 1-to-1 mole ratio. So then this gives us moles of copper sulfate. Then we can multiply it by the molecular weight of our anhydrous copper sulfate and get our theoretical yield. So I'm going to go ahead and punch that in. So 4.75 divided by 249.645. So we get that number, 1-to-1 mole ratio, and then times 159.6. And so then this is our theoretical yield. So if everything had gone as expected, and need to look at my calculator again. So 3.03, could have rounded it to 3.04 with that 6, so 3.04 grams. Oops. And so again, right, this is our theoretical yield. And then we can find our percent yield, so just dividing. So what we actually got, so divided by that theoretical yield. And so then we should get roughly 93% and keep the 3 sig figs, so 92.7%. And so on sig figs, again, you're just limited by what you're given in the problem. And so make sure you keep those sig figs consistent in the problem. That was really the biggest error that was kind of in the exams, just kind of thinking back to the exams. But overall, really good scores. You know, people are doing really well in this class right now, so I'm pretty pleased with y'all. So keep up the good work. All right, questions about this problem? And so let's just look at the lab. And so you kind of had to go through this and watch the video, and then it would take you through this. And then these calculations kind of take you through this. If you need help, though, let me know. And we can always go over them later. And so if you're in the chat, you can always, say hello or something if you want me to continue going over this. The only other thing that I notice is with your mole ratio, I think people are rounding kind of too much. So let's just pretend, because I thought someone had gotten like 0.019 as their ratio. And then it says like mole ratio expressed as a decimal. So I would have kept that number there. And then when it said rounded to nearest whole number, people rounded this to like 0. And what if we invert it though? And so then this gives us another ratio of 52. Maybe it's 0.19. Let's invert that one. And so you get like about a 5 ratio. Again, I don't quite remember the number, but now I'm just going to start playing with all the numbers. But you see how you invert it and you get a larger whole number. So that's the number that you want to report there. But it seems like most people figured it out for the actual formula part. All right, other questions about the lab or homework or anything? That was the main issue that I noticed. And so if you can understand this problem, I think you can do the rest of the kind of post-lab stuff. And see, post-lab mentions, calculating your yield. So this is based off of what you get and kind of figuring that out. But all the math is pretty similar to this question 1. But again, reach out individually if you need help. Or again, we can chat during this. All right, so now let's shift over to our next chapter. So this chapter is going to cover a bit of gases, so what those are, kind of our PV equals nRT equation. So we'll go into what that is, but that's kind of what I like to say is all you need to know for this chapter. And then the last bit of this chapter will be going into those intermolecular forces and then talking about that. All right, so let's see how far we get today. All right, so we have our gases, liquids, and solids. And so again, this should be general knowledge, but let's just go over it so we're all on the same page. So a solid, we say, has a fixed shape and fixed volume, or I would say determinate. Right, so we can't change that, or it holds its shape. And then a liquid, so a liquid has a defined volume or fixed volume as stated here. But of course, as you know, it takes the shape to fit your container, so you can pour it from one container to the next. And then if we compare that to gases, so remember gases expand to fill a container, so you can think about perfume, right? That liquid becomes aerosolized and goes throughout the whole room. Same thing, right? With any gas, it's going to mix. And so what is a gas? So again, this is our gas chapter. And so our gases they're defined as, of course, a phase of matter where our particles are moving randomly and very fast in our containers. And gas particles move in straight lines until they collide with either the wall or another particle, and they bounce off. And a gaseous atom or molecule exerts a force when it collides with our surface. So molecular collisions are pressure. All right, I'm going to be right back. I'm going to get some water for a second. All right. Apologize for that. All right. So back to gas pressure. So what is gas pressure? So pressure is just defined as the force exerted per unit area by gas molecules as they strike the surfaces around them. And so let's think about a balloon. So how does a balloon stay inflated? And so what's kind of cool about the balloon is that the balloon has to fight against the atmosphere. So if you think about our atmosphere, we have tons of collisions bashing down on our balloon. And so that means in order to stay inflated, right, the balloon particles have to be colliding on the inside and fighting against our atmospheric pressure to keep our balloon inflated. So then our gas pressure is the result of the constant movement of those gas molecules and their collisions. And so again, our pressure is our force over our area. So then we'll start to see, so if we were to, shrink our balloon, so then we'd have more collisions in a smaller volume, so smaller surface area. And so that would lead to an increased pressure versus a larger balloon, where then that area is spread out. And so then less force. And so when we talk about gases, especially in this chapter and right now, so we're applying the kinetic theory of gases, and we'll kind of talk about how this kinetic theory and this kind of idealized behavior of gases differs from reality. And so when we're talking about gases in our sense, we're assuming that our particles are very small, so they're occupying no space. We're saying that they don't have any interaction with each other, so no attractions either. Again, we'll learn the differences of reality. And so we're also assuming that all collisions are perfectly elastic. So what does this mean? So this means no exchange of energy occurs. So that means if two gas molecules collide, they just perfectly bounce off. Again, no exchange of energy. So inelastic, just for comparison, would be like in a car crash, where the energy of the crash goes into crumpling the car as opposed to, bouncing. And so now let's look at our pressure units and how they're measured. And so we said that our pressure was basically, right, our atmospheric gas molecules beating down. And so here we have our apparatus for measuring our atmospheric pressure or any pressure. And so here's our glass tube that's under a vacuum. And so then all these little collisions start driving the mercury up. And so it's driven up by however many collisions there are. And so again, this corresponds then to our 1 atmospheric pressure. And so the mercury would rise to 760 millimeters of mercury. Or, of course, you can just translate that to inches. So this is just a millimeter to inch conversion here. And then the other unit of atmosphere that you see often is torr. And so notice that millimeters of mercury and torr are the same. So you see those used pretty interchangeably. And 760 millimeters of mercury and 760 torr is 1 atm. And so we can see other units. So we have the Pascal. You might also see kilopascal. So that'd be 1,000 pascals. So that'd be kPa. So that'd be 101.325. Don't really use this too much, but again, it could crop up. PSI, this would be like your car. So like a typical, at least a small car tire is maybe around 33 PSI. So almost 2 atmospheres. Y'all in the chat, if you have trucks, you can always tell me what those pressures run at. So that's 14.7 psi is 1 atm. And then we might also see bar, especially if you look at like a local weather report, that's going to give the pressure in bar. Yeah, so there's our inches of mercury. Any questions about that so far? And so these are what we call kind of our basic properties of a gas, or how we can define our gas, how we can characterize our gas. And so a gas is always going to have a pressure. So what pressure is your gas in? And so when it says units here, this is going to be the unit for, let's say, our typical gas law equation. So PV equals nRT that we're going to be discussing. Right. So, and I'll point out when the units matter and don't matter. And so it tells you our typical units, again, for this formula would be an ATM. Our volume would be in liters for this formula. Temperature, now this is important because temperature always needs to be in Kelvin, even with our simple gas law formulas. And again, I'll point that out. And then our amount in moles. Then it didn't mention our gas constant here, but R is 0.0821. And that is for these units here. So liters, ATM, Kelvin, moles. And so we'll look at this and see that these properties are interrelated, and kind of how when changes, the other ones are affected as well. And so these are just kind of the simple gas laws. And again, let's go over them. So the first one starts with Boyle's law. And Boyle was just investigating this relationship of volume and pressure. And so they were playing with these J tubes, but essentially what they found was that if they increase the pressure, and so they added our a weight here, and so then the volume halved, and then they noticed that caused an increase in the pressure. So here we have our first scenario, and I'll zoom in here, that we had our volume of 1 liter, pressure of 1 atm, and then volume of 0.5 liter, pressure at 2 atm once they have that. And so they said this was an inverse relationship, because if one decreases, the other increases. And so then we end up with Boyle's law. So this is just a graph of pressure versus volume. And of course, it does level out eventually, and we do have physical limitations, right? And so in our assumption here, we said that, gases don't really occupy space. Obviously, that's not true. And so at some point, we do reach, our limit of compressibility here. And so the important part that we will parse out from this is, again, this equation. So this shows that they're inversely related. So again, you increase one, you decrease the other. And so in this case, I'll say that units don't matter. As long as consistent. And so all that means is, right, pressure could be in torr and volume in milliliters and milliliters. And that's fine, just as long as you're working with this relationship here. And has anybody gone diving? you've gone diving and you're watching later, you can always send me an email like, yes, that was me. And I've had some students tell me some kind of horror stories in the past, or semi-horror stories. And so let's look at diving and talk about this. And so it says for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure due to the weight of the surrounding water. And so now this kind of helps us answer the question as to why they always say, you need to rise slowly. And let's think about that. And so if a diver holds your breath and you rise quickly to the surface, right, the outside pressure would drop to 1 atm. And so by Boyle's law, right, that volume would also expand. And so that's part of why they say to exhale. But the other issue is really you're thinking about all the gases dissolved in your lungs, which cause issue. And so you have some nitrogen dissolved in your blood as well. And of course, there's oxygen. And right, so of course, when you're diving, that's compressed, all of that gas. And so if you rise too quickly, right, again, that gas can bubble out and cause damage to internal organs. One of my students, I think, was telling me, they were in the military and telling me some horror story of some guy they knew. They were diving and I think they weren't monitoring their oxygen. So they were kind of running out of oxygen and then they were coming up too quickly. And so I think they had some issues and maybe busted a few blood vessels. And then what's also fascinating, not to get you too much onto a tangent, but you could research the world of like competitive deep diving because they have kind of issues of this. And, you can obviously imagine what that entails, right? If you're a competitive deep diver, you hold your breath, dive really far down to the bottom, and then go back up, which is, completely incredible and crazy in some sense. But they do that, but some of them do suffer injuries, the more extreme ones, like they'll get, aneurysms or bust blood vessels because of this. So it's pretty intense. Anyways, I won't go too far down the rabbit hole. Let's try this problem. So as you breathe, you inhale by increasing your lung volume. So you can think about your diaphragm going down. So that physically increases your lung volume. So if you have an initial lung volume of 2.75 liters, which is filled at a pressure of 1.02 atm, if you increase your lung volume to 3.25 liters, and so right, just say that this is before the inhale, so right before, what is the pressure? All right, let's see how we're doing with this problem. And so we can use our relationship. So P1 V1 equals P2 V2. And the hardest part about these problems is just kind of establishing who's who. And so if you need to do that, do that. So we have our initial V1 and P1. All right, so now, and then we said this was our V2. So solving for P2. So now I'm going to sub everything. And It just so happens they were in ATM and liters, but in this case, again, it wouldn't have really mattered what the units were as long as we were consistent. And let's just see what we get with our calculator. There we go. And about 0.863 ATM. And that makes sense, right? So you're kind of thinking, and you always want to do a sanity check. So you were here increasing the volume. Okay, so that means pressure should go down. And it did. So that looks good there. And the next one we'll examine is Charles. This Charles's law. So this is looking at our volume temperature relationship. And so now we're saying that the volume of a gas at a constant pressure, and this is kind of key here, because it's saying we want to hold that pressure constant. And so that volume then is going to increase then with increasing temperature. And so this is important. So temperature has to be in Kelvin with this one. And so part of that is it has to have thermodynamic relevance. And remember, our Kelvin starts at 0. And we don't want to have a negative temperature because then that doesn't make any sense for us. And so while we're here, if you've never played with this, but I feel like most people have heard of this by now, these PhET simulations, these can be, fun to play with if you've never seen them. I feel like they used to use them a lot in high school. And so you do like the ideal relationship. So hold constant. I want to hold. How do I hold pressure? Hang on. I think I have to start this a little. There we go. So now I want to hold my pressure constant. And if we're exploring Charles's law, so we're holding pressure constant. We're at 3 ATM. And then now we have our heat. So let's increase our heat. And so notice, so I increased it a little. So you saw that box increasing, right? To keep our pressure. So let's kind of watch that. I wish I had a volume. I don't see a volume measurement on there. But you can just see the box. Yep. And then I maxed it out there. So that's always fun to play with. And so that might help you. And so what we find is we get this equation. So I'll kind of rewrite it, but we have V1 over T1 is equal to V2 over T2. And again, temperature in Kelvin, like star that, whatever you need to do so you don't forget. And so again, we're assuming that we have our ideal gas. And so according to our kinetic molecular theory, we increase our temperature of the gas. That means our average speed and thus kinetic energy of the particles. So kinetic energy is 1/2 mv squared. And then, of course, you have your distribution. And so the greater volume spreads the collisions out over a greater surface area, so our pressure is unchanged. Again, right, that's why our volume increased on this one here. And so then this graph is showing us if we could extrapolate all the way down to absolute zero for all these gases. And so, of course, the issue is, again, that all gases condense into a liquid. And so these assumptions here, these lines here, are not taking into account any intermolecular forces. And so that's kind of the difference between our kinetic molecular theory and, again, our true nature of gases. All right, let's watch this fun video too. Let me pull this up. I show this video in class as well because it's kind of fun. After showing this in class, I usually do a smaller demo, but this is cooler.
Hi, everybody. Jay Birschbach along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel. I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day. Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down. Okay. We should see some crushing action at that point. But first, we're going to need to heat that air up. Okay. So help me flip this up on our stand here. Okay. The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here. Sure. And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches. Yeah, I think I'll back up. All right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how
they really just wanted a big torch, but...
There's a good sort of jet of...
All right, so this is pretty important here. So let's just kind of recap what they're doing. So they're trying to take advantage of the fact that water easily goes through those 3 states, right? Well, here we're just looking at liquid and gas, but it goes through them at a relatively, mild temperature range, I'll say. So like, liquid nitrogen would be a lot more difficult to recondense back. And so the idea is, so now they have this small amount of water, right? They heat it up, so now it's at its gas phase, and then they want to seal it up and trap it, right? So you have basically less molecules of gas trapped in here, right? So once we cool it back down, less molecules, and then that's really going to decrease that pressure on the inside. So let's watch.
Steam is shooting out, but we're going to try to capture that. Okay. By putting the plug back in.
So closed system.
Wrench it down tight because we don't want any of that warm, expanded
again,
air
closed system.
But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to spin it down.
And so think of that water, right, condensing back down to liquid.
There we go. There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside has cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can. Or if you ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Yeah, so if you've never observed that with the milk jugs that he was talking about, right? Rinse one up again, seal it, and then once you have that closed system and it cools, you notice it shrink. And so that's kind of what's going on here in this bath. Obviously, it's not as exciting as what we just watched with the video. But if we take our balloon, so just like a normal sized balloon, and again, this is what I sometimes do in class, is I put it in some liquid nitrogen, then you watch it shrink, then of course take it out and it goes back out again. So same thing, right? You could put, and this is something you could do at home, just take your balloon, put it in some ice, watch it shrink a little, and then take that same balloon that you made at room temperature, put it in some boiling water, and see if you notice it expanding. All right, let's try our next sample problem. Again, don't forget to convert and be in Kelvin. And let's give you the formula one more time. So remember, it's V1 over T1 equals V2 over T2. And so we have a sample gas has a volume of 2.8 liters at some temperature. When we submerge the sample in ice water at 0 degrees Celsius, its volume decreases 2.57 liters. What was the initial temperature? So again, I'll keep moving, but feel free to pause if you need more time. Definitely don't rush. And so again, just setting up what's what. So we have our V1 and we don't know our T1. And then we have V2 and we have T2. But then T2, we want to add 273. So it's in Kelvin. So that should be our T2. So now I'll just start setting up my equation. And then cross multiply and solve here. Once I pull my calculator back up. So 2.8. Let me just clear this. 2.8 times 273. And then divided by 2.57. And so then we get a temperature. So T1 is 297 Kelvin. And then let's subtract. So minus 273. I'll do the 0.15 just to see where we round up. So it's still about 24. So that's 24 degrees Celsius. Questions on this one? All right, let's continue with our last kind of relationship. And we'll look at the combined gas laws. And so this one is pretty self-explanatory. It makes sense, right? Kind of the more moles you have, well, if you're keeping pressure and temperature constant, and again, that's always kind of the key, right? You're only looking at two variables. The other two variables are being held constant. And so that means If moles is increasing, then of course our volume will have to increase. And this is nice. So we'll assume this. So equal volumes of gases contain equal number of molecules. So again, the identity doesn't matter. So in actuality, there's a little bit of variation depending on the gases. And I think we'll kind of discuss that later. For our purposes, again, or assuming ideal gases, so the identity does not matter. Then that leaves us with this equation. So V1 over N1 is equal to V2 over N2. So again, they're directly proportional with this equation here. It's showing that. And so again, Avogadro's law is just stating that our volume is proportional to the number of gas molecules holding pressure constant. All right, let's try our last practice problem. And I'll rewrite the formula for you. So a student in a kinesiology research has a lung volume of 6.15 liters during a dip inhalation. At this volume, his lungs contained 0.245 moles of air. During exhalation, the lung volume decreases to 2.55 liters. And so watch what it's asking. How many moles of gas does the athlete exhale during exhalation? How's the problem going? Again, I'll start going through it. Feel free to pause or continue working as I work it. So again, we had our V1 6.15 liters and initially 0.254 moles. And then we decrease 2.55 liters. And then it asks for exhale though, but we need to figure out, well, how many remained? So time to cross multiply 2.55, oops, times 0.254 divided by our 6. And so we have 0.105 in the lungs, so that was X. But it was asking for exhale, so that was kind of tricky. So we had to read what it was really asking. So now we do 0.254 minus this answer to figure out how much actually remains. And so that leaves us with 0.148 moles exhaled. Questions on this problem here? And so this leads us to our ideal gas law. And so this is kind of nice. So this, I would say, is the only equation we need to know. So again, this is where the pressure has to be in ATM, volume in liters. Then we have our N in moles. R is our gas constant, 0.0821. And then temperature in Kelvin. But let's go through this derivation. Actually, let's talk about some other things. So if you just type into Google, and let's do that together. So gas law constant. And let's just look at Wikipedia. And so if you notice, oh my goodness, right? There's all these different R's. Well, how come they're different from the one we're using? And so look at the units that correspond to it. And so the one that popped up on what we'll say, right, the AI feature, nothing's AI. That one has to do with energy. And so we might see this later in the class. So this is joules, Kelvin, moles. So not what we're interested in. And if so, we go down and, oh, here's the one we are familiar with, liters, ATM, Kelvin, moles. And there it is, 0.082. And they take it out too much further than what we use. And some people like using 0.08206. That's fine. I usually round mine to 0.0821. And that's kind of considered maybe like the smallest, the least precise value you can use. This one. So I'll just highlight that. All right. Does that clarify where that gas constant came from? I don't want anyone confused. I don't want anyone confused when you Google that. All right. And then it tries to walk us through the derivation, but I think it makes it kind of confusing. So let's run through it together. And so we're starting with PV equals nRT. And R is a constant, so we can rewrite it to this. So R is PV over NT. And if R is a constant, we can set P1 V1 over N1 T1 to equal R, which is also equal to some other condition of P2 V2 over N2 T2. And so then this leads us to the other form of the gas law that I like, which is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And now this is nice. So this is kind of the combined ideal gas law. And again, we can derive all the ones that we just talked about. So there's our P1 V1 equals P2 V2, right? If we hold the other variables constant. And so that's the key, right? Is that we can cancel out variables that are constant. So that's why a problem may say, you know, at a constant pressure, at a constant volume, whatever. And what's also nice is you can kind of derive other variations of the PV equals nRT. And so sometimes you'll see that. So I think you have like P1 V1 over T1 equals P2 V2 over T2. Oops. And that is just holding, right, N constant. And this means you can solve a problem where 3 variables change. And so this is really, really quite powerful then. And again, we can see all the other laws. So there's our V1 over N1 equals V2 over N2. And V1 over T1 equals V2 over T2. So again, they're all there. You can kind of highlight them just so you can really see that. And so here they kind of re-show this. And we're holding those constant, and we would get out those laws we just discussed. All right, let's try this one. And again, I'll just give you PV equals nRT. So maybe we need this one, but if it's variables changing, then I would just switch it to this form. So these are really the two formulas you need to know for this chapter. All right, so I'll let you try that one. All right, let's see how we're doing. So it says calculate the volume occupied by 0.845 moles of gas at a pressure of 1.37 atm and a pressure of 315 Kelvin. And so this sounds like it's going to be a PV equals nRT equation since we're not given any initial or final conditions. And they were super nice and they already gave it to us in moles, Kelvin, ATM, so we don't need to convert. So we can go ahead and plug everything in. So pressure, and we want to solve for volume, so we can go ahead and arrange. And so then we're given 0.845 times our constant times our temperature divided by our pressure. So now I'm just going to punch this in. So just double check me, please. All right. So divided by our pressure. And then our volume should be in liters. So 15.95 liters. Any questions about that? And so the last bit of thing we should go over is the standard conditions, or STP. And so this is really nice. And there are a couple of things to know about this. So we define our standard conditions as 1 atm, 0 degrees Celsius, 1 mole. And then this means, and again, this is really important, so let's kind of highlight this. So all gases, we said, occupy the same volume. And so the standard volume is 22.4 liters. And so that means that we have now a new molar conversion. So we can say 1 mole of gas always occupies 22.4 liters. So this is really important. This is super useful, right? This also tells us 6.022 times 10 to the 23rd molecules of gas, right, are in 22.4 liters, again at STP. So you might see word problems using these relationships and bits of information to try to trick you up. And so again, our molar volume in STP, and I would highlight this, star this, whatever you need to do so you can remember this. And we said, so our volume of 1 mole at STP is our molar volume, corresponding to our 6.022 times 10 to the 23rd molecules of gas. And we said the type of gas does not matter. I thought I had a graph here, but I don't have it in these notes. But again, I just want to emphasize in reality, right, there's a little bit of differences, but actually for the most part, they're pretty close to 22.4 liters. And this mentions, right, even though they have the same volume, right, they have different masses. So they have different identities. And so they would also have different densities. So that could be a property that you might be thinking of. And, right, just think like helium. So that would be less dense than our xenon, right? So helium is only 2 grams per mole for the molecular weight versus xenon, which I don't have my periodic table. There we go. P table to the rescue. So xenon, right, is a lot heavier. Oh, sorry. Helium is 4 versus xenon's 131, but still a huge difference in mass. And so, right, don't forget. Sorry, I don't mean to jump so much. So density is, of course, mass over volume. And so just think of helium. So 4 grams per 22.4 liters versus xenon, which is 131 grams roughly for 22.4 liters. Questions about that there? All right. Let's at least talk about this. I was just trying to remind myself how much partial pressure problems you actually have in this class. And so Dalton's law states that our total pressure of the gas is the sum of our partial pressures. And that goes back to, right, our kinetic molecular theory. We said that the identity of the gases doesn't really matter. And so again, average kinetic energy is the same, and the total pressure would be the same. And so then we can add up our pressures. So this is just saying, again, right, pressure is additive. And let's put this in the context of something we know. So this is just kind of proving why, but I don't think we need to get into that. And so we have what's called this mole fraction. Sorry, I'm like squirrely today. And so our mole fraction, let's define what that is. So that's just moles of, let's just say, A over our total moles. Right? So this could be A plus B, or, you know, A plus B plus C plus D, whatever, however much. And so we have our mole fraction. And so then our mole fraction times our total pressure gives us our pressure of our component. So again, this is just mole fraction. So moles of A over total moles, or again, whatever you're interested in. And so let's get to the relevant information. And so you may know this. So air, let's talk about the composition of air. So, right, we have air at a total pressure of 1 atm. And then that's made up of 78% nitrogen. And so that's cool, right? Most of the air is actually nitrogen. And then 21% roughly is oxygen, so what we breathe. And then the other major component is argon. And of course, right, there's other gases, CO2. I think CO2 is like 0.4%, and methane, other trace gases. But those are the relevant ones. And so they've done the math for us over here. But we said, so this is our percentage. So this could be our mole fraction. And so all they did is we take 1 ATM times the composition, so times our percentage, 0.78. And so that gave us 0.78 ATM for our pressure of nitrogen. And then that would correspond to 0.21 for oxygen and 0.01 for argon. And then again, all other trace components. Questions about this one? Oh, and I meant to look at your homework. I'm just checking your homework for any partial pressure questions that we should review. But I just see a lot of PV equals nRT stuff. Yeah, I don't think we do too much in this class, so I think this is a good overview. All right, I think this is a good stopping point. So then on Wednesday, we'll look at state changes and the intermolecular forces between them and kind of talk about, okay, we had our kinetic molecular theory where we assume no interactions, but let's talk about what happens in actuality and what we observe and then why that is. So that will be Wednesday's lecture. All right, so again, recap. All you need to know really is PV equals nRT, and of course our standard conditions, and right, STP. So I'll just add that. Right, so no at STP, 1 mole, 22.4 liters. So that's just kind of our need to know on this page right there. So I'll leave that as our need to know. So if you have questions, let me know. I'll stick around in the chat. If you want me to go over something, just put that in the chat, a homework problem, a lab question, anything. Otherwise, you can catch me by email and and then we can make an appointment either in person or over Zoom, whatever is best for you. All right. Thanks again. I'll hang around on stream. Otherwise, catch you over email.